Hey, night owls! Welcome to another episode of Later Than Late Night Talks with Steffi and Carly. I am Carlo.
And I am Steven. We're your hosts for this late night rendezvous filled with laughter, insights, and maybe a few unexpected surprises.
Well, how's your day today, Steffi?
Well, so far so good. How about you, Carlo?
Hmm, it's great. My day's okay. I'm chilling with my favorite brew here.
That's a great pointer for our current episode today. Speaking of brewing, have you ever noticed how blowing on a cup of coffee cools so much faster compared to just leaving it on the table? Well, in theory, what you're unconsciously doing is employing forced convection to cool your coffee faster.
That's a great introduction for our episode for today. Well, today we will just focus on the external parallel flow over a flat plate. Oh, well, let's talk about the principles behind it. First, the heat transfer in external flow. External flows are just flows over bodies immersed in fluids that flow over the boundary layer in one direction that involves no velocity and temperature gradients. This flow is opposite to the internal flows which are surrounded by solid boundaries. Example of the internal flow is the pipe flow. The flow fields and geometries for most external flow problems are too complicated to be solved analytically, and thus we have to rely on correlations based on experimental data. Okay, so example of external flow is as seen in this figure, the flow of air around airplane. The flow is also responsible for numerous physical phenomena such as the drag force acting on the plane, which will be discussed later, the lift developed by airplane wings, the upward draft of rain, snow, hail, and dust particles in high winds. Okay, so let's proceed to the drag force. It is common knowledge that a body meets resistance when forced to move through fluids. In the previous example, the air pushed the plane back, like we experience when we extend our arm out of the window of a moving car. The force a flowing fluid exerts on a body in the flow direction is called drag. The phenomena that affect the drag force also affect the heat transfer, which can be seen in the Nusselt number. The relationship is shown in the function below, where the Nusselt number at certain x is a function of x, the Reynolds number, and the Prandtl number, or the average Nusselt number is a function of the Reynolds number and the Prandtl number. Okay, so the relationship can be further shown in a power relation form, which is Nusselt number is equal to the value of constant C multiplied by the Reynolds number raised to m and multiplied to the Prandtl's number raised to n. So the constancy depends on the geometry and the flow. And note that the m and n are constant exponents. The fluid properties are also vary with the temperature. The equation below is called the film temperature, which is obtained to account for the variation of fluid properties with temperature. It is the arithmetic average of the surface and free stream temperatures, and these fluid properties are then assumed to remain constant at those values during the entire flow.
Okay, so we now proceed to parallel flow over flat plates. So the flow starts out laminar but becomes turbulent if the plate is sufficiently long. And this is seen in the figure on the right where the parallel flow of a fluid over a flat plate of length L. And the x-coordinate is measured from the source of the fluid to the direction of a point in the plate in the direction of flow. And the velocity is considered uniform, and as you can see in the figure, the flow in the velocity boundary layers starts out as laminar but becomes turbulent as the plate gets longer at the distance, which is xcr, and this is also at the critical Reynolds number. And consequently, the flow transition depends on the surface geometry, roughness, temperature, upstream velocity, and type of fluid. Okay, so in order to proceed with the calculations, we must first review ourselves with the fundamental dimensionless numbers, the first of which is your Reynolds number. So the formula is shown here, where the Reynolds number at length x in the plate is just density times the velocity times the length x, and then divided by the dynamic viscosity. This is also equal to the velocity times the length divided by the kinematic viscosity, and by calculating the Reynolds number, we can classify the flow into three types: laminar, transition, or turbulent. So the flow is considered laminar if the calculated Reynolds number is less than 1 times 10 raised to 5, and is considered transition if the flow is from 1 times 10 raised to 5 to 3 times 10 raised to 6, and is considered turbulent if the flow is greater than 3 times 10 raised to 6. Alright, so here we have the concept of the critical Reynolds number, which is the value as the flow becomes turbulent from its laminar state. However, in engineering analysis, there is a general rule of thumb, and the accepted value for the critical Reynolds number is 5 times 10 raised to 5. However, this varies from 10 raised to 5 to 3 times 10 raised to 6, as it depends on the variation of pressure, surface roughness, and turbulence level. And we also have another dimensionless number called the Prandtl number, which is the dynamic viscosity times the specific heat capacity, which is then divided by the thermal conductivity. Okay, so finally we have the Nusselt number, which is a function of the Reynolds number and the Prandtl number. The formula of the Nusselt number is denoted by the convection coefficient times the length divided by the thermal conductivity, and the calculation of the Nusselt number in external parallel flow over flat plates can be calculated in two ways. The first method is to calculate the local Nusselt number at a specific location or length x, and this can be done for either laminar or turbulent flows, and their conditions are shown on the right side, where, as you can see, the Prandtl number and Reynolds number for laminar flows must be greater than 0.6 and less than 5 times 10 raised to 5 respectively. Furthermore, the Prandtl number must be between 0.6 and 60, and the Reynolds number must be between 5 times 10 raised to 5 and 10 raised to 7. And as you can notice, the coefficients and the exponents of the formulas that include the Reynolds and Prandtl numbers are different depending on the type of flow. And the second method to calculate the Nusselt number is to calculate the average Nusselt number for the entire plate. So there are also certain requirements for the range of the Reynolds number of the entire plate and the Prandtl number. For laminar flow, the Reynolds number must be less than 5 times 10 raised to 5, and the Prandtl number must be greater than 0.6. For turbulent flow, on the other hand, the Prandtl number must be within the range of 0.6 to 60, and the Reynolds number of the entire plate must be between 5 times 10 raised to 5 and 10 raised to 7. And once again, when looking at the equations for the Nusselt numbers, the coefficients and exponents change for each condition, whether they are laminar or not.
Well, what an informative discussion. This episode is truly an unexpected surprise. Oh no! Steffi, I just spilled my coffee on my iPad. What will I do?
Oh dear! Carla's coffee mishap resulted in a spill on his pristine iPad Pro Max 900S. The coffee, freshly brewed and at Carla's preferred temperature, reached a toasty 75 degrees Celsius. In stark contrast, the iPad's surface was at the ambient room temperature of 25 degrees Celsius. After swiftly tending to the spill, the iPad's temperature dropped to around 60 degrees Celsius, dangerously close to overheating. Carla needs to cool down the iPad to avoid further damage. Looking around the room, he decides that he can place the bottom of the device directly beside the air conditioner, set at 15 degrees Celsius so that its airflow with a velocity of 4 meters per second would help the iPad cool down even faster. While waiting for the device to cool down, he got bored and proceeded to calculate the convective heat coefficient and the rate of heat transfer in the system because he is an A+ student of Dr. Promantilla. He called Steven to ask for details regarding the properties of the iPad, with a thermal conductivity of 17 watts per meter Kelvin, a length of 26 centimeters, and a width of 17 centimeters, and a cool air with a thermal conductivity of 0.0225 watts per meter Kelvin.
Alright, so let's try to solve this problem. So here we have the given. The temperature of the surface is 60 degrees Celsius. The fluid's temperature is 18 degrees Celsius. The velocity of the fluid is 4 meters per second. The length of the surface is 26 centimeters or 0.26 meters. The width is 17 centimeters or 0.17 meters. And since the problem states that the bottom of the iPad is directly beside the air conditioner, it is safe to assume that X is the length of the device, which is 0.26 meters.
Alright, so before you proceed with any more calculations, you must first calculate the film temperature. So why do we calculate this? This is done to account for the variations of the fluid properties with temperature. So we get the film temperature by adding the temperature of the surface and the temperature of the fluid and dividing them both by 2. This results in a film temperature of 39 degrees Celsius. After doing so, we get the properties of air at the film temperature. So these values are sourced from Jacopolis after a few interpolations, resulting in a density of 1.2146 kilograms per cubic meter, a dynamic viscosity of 1.81 times 10 raised to negative 5 kilograms per meter per second, a specific heat capacity of 1.0048 kilojoules per kilogram per Kelvin, and a thermal conductivity of 0.0225 watts per meter per Kelvin based from the given in the problem.
Now that we have all the necessary information, we can now proceed to calculate the Reynolds number and the Prandtl number. We need both of these dimensionless numbers to calculate for the Nusselt number, which we will be using to solve for our convective heat coefficient. So for the Reynolds number, we can just use the formula density times velocity times the length all over the dynamic viscosity, which results in a Reynolds number of 69,789.1713. Next, we can then proceed to calculate the Prandtl number, which is the dynamic viscosity times the specific heat capacity divided by the thermal conductivity, resulting in a value of 0.8083. After that, we can now finally calculate the Nusselt number. As discussed previously, the formula of the Nusselt number is dependent on whether or not the fluid is considered laminar or turbulent. Since the Reynolds number is less than 5 times 10 raised to 5 or 500,000 and the Prandtl number is greater than 0.6, we can proceed to use the formula 0.332 times the Reynolds number raised to 0.5 times Prandtl number raised to 1/3. The result in a Nusselt number is 81.7004.
And after obtaining all of the fluid properties, the Reynolds number, Prandtl number, which is used to obtain the Nusselt number, we can now use the correlation to obtain the convection coefficient. And as you can see, this is just the thermal conductivity times the Nusselt number all over the length. And this results in a value of 7.0702 watts per meter squared per Kelvin. And with the convection coefficient now solved, we can now proceed in the calculation of the rate of heat transfer, which is the convection coefficient times the surface area times delta T. The surface area here is just 26 centimeters times 17 centimeters based on the given, and now calculating for Q, we have 13.1252 watts, which is the rate of heat transfer of the system. And now, we have finally solved the problem.